Welcome to topic 9 of reviewing for the SOL. This week we're going to be talking about similarity. Remember, when you're dealing with similarity, you are looking for angles that are congruent and sides that are proportional. If you use a similarity statement, for example, triangle ABC is similar to triangle DEF, what this statement, this similarity statement tells you is what angles are congruent and what sides are proportional. Here's how. Remember, angles only get used by one letter. So what we know here is the first one here, A, will be congruent to D. So angle A is congruent to angle D. And so on. B will be congruent to E. C will be congruent to F. We also know what sides will be proportional. Sides get named by two letters. So the first two letters here, AB, which is a side, will be in proportion, meaning like a ratio, a fraction, with DE. So we know the ratio of AB to DE is the same as the next two letters, BC to EF. And similarly, if you use the first and last letter, meaning the only other two that are next to each other, if you draw it out, you find that AC will be in proportion with DF. Now, this is a lot to try and find for every single example. So we learned some postulates and theorems, some shortcuts that told us we don't need to find all this information. What we need to find are a few specific things. For example, angle. That's exactly what it sounds like. We are looking for two angles that are congruent. Finding that will be enough to figure out if the triangles are similar. So, first thing I notice right here with this example, angle L is congruent to angle X. That is one pair of angles. We need two. Well, 45 and 50 are not the same, but what we know about triangles is they add up to 180 degrees. It doesn't matter which triangle you use, but if you take 180 and subtract away 85 and 50, you find out that there are 45 degrees right here in angle Y. Now, here's what I notice. This gives us our second pair of angles, and we could prove these two triangles are similar by using angle. So just like you needed to prove the angles are congruent, here with side, you need to show that they are proportional. And what you are looking for is a scale factor, some ratio, some fraction that all these sides have in common. Some of you are looking at this going, I don't see how to match things up. When you are dealing with side, you want to think of small, medium, and large. What do I mean by that? Just look at one triangle at a time. Which one of those sides is the smallest? Yep. How about over here? Which side would pair up with it, because this would be the smallest side as well? Yep, right here. So we need to check and see if AC and DF have the same proportion of all the other sides. I'm just going to write this down for right now. 18 comes from AC, 24 comes from DF. If we focus, we just did the small sides, let's look at the medium sides. So which one is next biggest on this triangle? It would be side AB with a length of 21. And over here, 28 would be the next largest size. So we need to see if that proportion or ratio is the same as this ratio. So 21 over 28. And check the last set of sides. Well, there's only one left. It's 33 and 44. And before panicking, plug all these into your calculator. Hit math, enter, enter to simplify those fractions. What do we get? When you enter all of these in, each one, before you turn it back into a fraction, uses the same decimal of 0.75. We never want decimals when we're dealing with similarity. You always want to put it back into a fraction. The cool thing about this is each one of these uses the same ratio of 3 to 4. 3 to 4 is our scale factor. That lets us know how much larger this triangle is than that triangle proportionally. Because this ratio is the same for all three, not only is that the scale factor, but that proves that these triangles are similar by side. So angles, you always want to try and prove congruent. Sides, you always want to try and prove to be proportional. If you have side, angle, side, the two sides you have to be proportional. So let's use a little bit of highlighting here. We need to show that ST and VW match up with TU and WX. That's what this proportion is saying. And we can't actually simplify it. There aren't numbers here, but this is the basic idea. We also need our angle that is in between or included to be congruent. And it has to be that the angle is in between the two pairs of sides. Otherwise, it's not side, angle, side. It has to be in between, included between your two sides. So these are the three shortcuts, and they're really easy to remember, and they're really easy to work with. So please, when you're working with proofs, there's only three ways you can end a similarity proof. Angle, angle, side, 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 and side, angle, side. Another type of example of these, you are given a similarity statement. You know this. This tells you you are similar. Don't forget that symbol right there. Just the squiggle means similarity. If it's got an equal sign, that's when we're talking congruent. So, given all of this information, we have a whole bunch of sides here and a whole bunch of sides here. We don't have any angles, so knowing sides, they need to be proportional. So the first thing I notice is AB, first two letters here, is going to be proportional with LM, the first two letters here. Why did I pick these two? Because they're numbers. They simplify as a fraction. If you try plugging in x plus 5, 3x plus 3, you can't simplify that unless you know what x is. So let's start by simplifying the two sides that match up that are both numbers so we can find the scale factor. You plug 5 over 10 into your calculator, hit math, enter, enter. We know the scale factor is 1 to 2, comparing this triangle to this triangle. Well, let's finish reading the rest of this question. What is the length of AC? If we're going to try and find AC, let's use this AC in the problem. It matches up with AC, matches to LN. So we are checking to see that these sides are in the same ratio as these sides. And the easy way to do that, we've already found the scale factor. Use this number. Your scale factor in simplest form, always makes life a little easier, can be used to set up a proportion so we can cross multiply and find x. Here's what we know. We know the scale factor is 1 to 2. We were comparing this triangle to this triangle, so the small one to the big one. So we need to use this side, x plus 5, divide by this side, 3x plus 3. Now what I would do is put parentheses whenever you're adding or subtracting. That way you remember during your next step, which is cross multiply, to distribute. So you get 1 times 3x plus 3 is equal to 2 times x plus 5. Distributing the 1, well, 1 times anything will give you the same thing it was. So 3x plus 3 is equal to 2 times x is 2x, 2 times 5 is 10. From here, all you got to do is just solve. I'm going to move my 2x over, subtract from both sides. I want to move the 3 over as well, so I'm going to go minus 3 from both sides. Then add down. 3 minus 2 gives you 1x. 10 minus 3 gives you 7. Be sure to look back at the problem. It didn't ask you what does x equal. We want to know the length of AC. Well, we now have x. Let's plug it in. If x equals 7, 7 plus 5 gives you 12. And that is the length of AC. So again, when you see these problems, don't panic because there's so many variables. Don't panic because of everything. If you're given a similarity statement, you know what matches. Pick two sides, one from each triangle, that have just numerical values. You don't want any variables yet. When you find those, simplify them and you get the scale factor. This scale factor can be set equal to a ratio of any two sides that you know are similar. Then you cross multiply and solve for x. In this problem, we had to go and use x in the end. Some problems you're done as soon as you get to x. The table. One of the easiest problems we could do all year. Every single time you do the exact same thing. I'll explain more about what belongs in these in a moment, but I'll explain how you navigate this table. If in one of these types of problems, if you aren't already here in the far left column, this is what we call the everything else column, you want to find these numbers first because it's easy to manipulate this ratio, which can also be written side by side. This ratio is the same as 2/5. But when you're in this table, it makes more sense to write it side by side. So what do we do? Length is one-dimensional. Any sort of area which belongs in this column is two-dimensional. Any sort of volume which belongs over here is three-dimensional. In order to change from different dimensions, what you're going to have to do is really simple. These two numbers moving to this column, dealing with area, square both of these. You're going from one lengthwise dimension to two length times width. This ratio doesn't make sense because in one dimension that's perfect, but in two it doesn't make sense unless you square them. So here's what we do. 2 squared, 5 squared, which is equal to 2 squared is 4, 5 squared is 25. And this is the ratio that belongs right here, 4 to 25. With volume, a three-dimensional object, again, 2 to 5 makes sense in one dimension. That's a straight line. This has length and width and height. So if I could draw a little cube, which you guys don't want to see me do, it's terrible. But promise me when I say that this would be like a cube, this is like a square, and this is like a straight line. You're getting more complicated. We need to do more things. So take this 2 to 5. Because we're going from one dimension to three dimensions, just like before, if you wanted to end in 2, you have to square it. If you want to end in 3, take your original ratio and cube it, right? 2 cubed is 8, 5 cubed is 125, and that is our ratio from one to the other in length, in area, and in volume. Well, why do we call these only area and volume, and why is this everything else? Well, the only thing that can belong in this column has to use the word area. So if you just see plain old area, lateral area, surface area, these things will belong in here. You can see right here, this problem, we'll get to that in a second, deals with surface area. So that ratio would be dealing with surface area. Any sort of thing where you have to see the word volume is dealing strictly with three dimensions and taking up space. So this V, again, we'll get to that problem in a minute, is strictly dealing with volume. There are a list that is a mile long that we could put here for lengths. For example, it could use scale factors. We could be dealing with a side. We could be dealing with a perimeter. We could be dealing with altitudes. We could be dealing with a height. I don't want to keep going because, again, I'm running out of space and I've got plenty more ideas. My point is, you have to see the word area to put anything in this table. You have to see the word volume to start on this spot of your chart. Everything else belongs here. So that's really important to note. Now, we did the easy version where you start with this ratio and you move to the more complicated ones. What if we start here? Well, it makes sense that we square this to go in this direction. Well, it would probably make even more sense to do the opposite of that going backwards. Well, it's the opposite of squaring something. That's right, square root. So here we would do the square root of 9. Compare that to the square root of 4. The square root of 9 is 3. Square root of 4 is 2. And take a look. We are now back in the column we want to be, in the everything else column. That means we already know how to end up at volume. We do the same thing we did up here. Cube both of your numbers. You're going from one dimension to 3. So 3 cubed, compare it with 2 cubed. You get 27 to 8. Same idea when you're down here. If you are in this part of the chart, we are already cubed compared to our original everything else, our scale factor. So to undo a cube, cube root those two numbers. The cube root of 216 compared to the cube root of 64. if you've forgotten where the cube root button is on your calculator, hit the math button, pull up the math menu, and you should see it staring right at you. I believe it is number 4. So when you cube root 216 and you cube root 64, you get a ratio of 6 to 4. Believe it or not, this can be simplified to be the same as 3 over 2. Math, enter, enter, if you don't believe me. So we already know 3 over 2, this is the most simplified. We could go back and fix this by plugging the fraction 216 divided by 64 and hitting math, enter, enter. So squaring this, again, 3 squared and 2 squared will give us the same 9 to 4 ratio. So that's how you manipulate numbers in this chart. But more often than not, you're going to get an example like this, where you've got a whole bunch of information about 2 different shapes that you know are similar. Well, if you're comparing surface area, volume, everything else, it doesn't matter. Set up a chart. First thing I noticed, because we don't know solid number 2's surface area. In fact, when we find that, we're done. We're going to call this x. If we're comparing this to this, that means the ratio of SA, surface area, area belongs right here. We know this is 100 over x. We can't do anything more with that yet. We're going to need to find our scale factor. We're going to have to find whatever 2 numbers that this ratio is to set this equal. What we do know is we've got some volume. We have 2 numbers here. And again, we compared from the left to the right. Do the same thing. 9,000 divided by 4608. And a lot of you are going to wonder, what should I do with that? Well, use your calculator. Plug it in. See what you get. As soon as you type in 9,000 divided by 4608, you get a really gross decimal. But hitting math, enter, enter simplifies this to be 125 over 64. Now, this is our ratio of volumes. We need to end up with the ratio of areas. So just like up here in this chart, we need to go back to square one with everything else. Then take the ratio we find here and square it. So let's take this and cube root both 125 and 64. When you do that, we end up in the everything else part, and we find that 5 to 4 is the ratio for everything else, or 1 dimensions. We need it for 2, so we take this and square it. 5 squared is 25 over 4 squared, which is 16. And now, because we know the proper ratio that belongs here, we can set it equal to this ratio in a proportion and cross multiply. So we're almost to the end. Cross multiply. 25 times x equals 16 times 100 is 1600. Divide, and you get x equal to 64. Well, 64 what? Let's go back. We are dealing with square miles in surface area, so there's your answer. Let's try a few more example problems here. These are a lot like the SOL style, and we are almost done. Stick with me. We need to look at this triangle and figure out which one over here it is similar to. Well, we're going to have to find a scale factor that works. So here's what I would do. You can compare the short side to the short side and the long side to the long side for all of these, or let's try something a little different, which will also work. If we compare this short side to this long side, and realize it doesn't matter which one we pick, 2 of them are the same, let's see what that ends up being. So 4 over 5.5 equals, I'm not even going to hit math, enter, enter on this, folks, and let me show you why. You get 0.727272. If you haven't checked it on your calculator yet, trust me, it's a repeating decimal that goes on forever. Now, why did I do this? Because if I know the ratio of the sides on this triangle, the small to the big is 0.72 repeating, I need to find that over here. So let's take a look and see which one of these either would work or just don't make sense at all. So here, this triangle, it has 1 short side and 2 long sides. Well, letter C has 3 different sides altogether. there's no way it's going to be proportional because you don't have three different sides here. You have two that repeat and one here. C is out. Over here, the longer side is the one that we have two of. Here, 4 is smaller than 5.5, so that's not going to work either. You needed to have two 5.5s and only one 4. And again, that's not what we're looking at here. So just by looking and thinking for a sec, we've eliminated half the answers. So now let's try this again. We need to compare the short side to the long side. Here, if you do 3 divided by 4.125, you get, hey, take a look. It's this 0.72 repeating. That means this is our answer. Now let me finish. I just want to go here and show you that 3 divided by 5.83, when you plug that into your calculator, you get, oh, this decimal is disgusting. If you don't believe me, check it out. 0.51457.9. The rest doesn't matter. You see this? It's not this. It's wrong. We are looking for what is similar. The ratios of sides have to be the same. Letter A. Answer is this one. In problem 2, we are told that Q lies on PR, S lies on RT, and we need to show that these are similar triangles. This means we need to either make angle-angle work, we need to make side-side-side work, or we need to make side-angle-side work. I can tell you right now, there's no numbers, no information at all here. So we are either going to be given one angle is congruent to another angle, or we get two sets of sides. So let's see if we have any information in this triangle that could help us. Here's what I notice. Both of them use R, meaning they both have angle R inside of them. And if they both have angle R, that's not going to change shape or size. We already have one congruent angle. So because we have one congruent angle, we don't know anything about sides. The most number of sides we are going to get is 2. Let's eliminate side, side, side. That's off. Let's see if we can make angle, angle work. So that means because we have one pair of angles, meaning R is congruent in both triangles, we need to show that P is congruent to Q here, or we need to show that T is congruent to S here. Now, I'm being lazy. This is not really Q. There are too many angles around here to just call this one Q. This is really RQS or SQR. That's Q. And for S, which again, I'm not calling that angle S because this could be angle S, this side could be angle S, both of them put together could be angle S. But what we want is this part right here, which is QSR. So if we can prove that the two that we have matched up are actually congruent, angle, angle will work. If not, we're going to have to go and figure out sides, angle, side. So let's check real quick. PQS, that's here. That wasn't any of the angles that I just showed, and it's actually not a part of any of the vertices, meaning the corners of these triangles. We can finish reading this. TSQ is down here. That doesn't help us at all. Letter F is out. Let's check here. PTR, congruent to TPR. Oh, that almost would have worked, but the two angles that we have here and here are only a part of the big triangle. Like we said, P has to be congruent to Q, RQS, or T has to be congruent to this angle down here, QSR. So, unfortunately, the easy one, angle, angle, is out. So we're going to have to find a way to make side, angle, side work. Well, if it's going to be side, angle, side, it has to be this side and this side compared to this side and this side. We might not get all of these in the same order, but we need these matchups. Let's see if we get them. QS. Ooh, QS. This isn't going to help us. If it's going to be side, angle, side, we need the two sides with the angle in between them. I can eliminate immediately. H. Let's look at J. QR compared to PR. Ooh, both blues are color-coded. SR to TR. Very good. This one ends up working. Letter J will show that these two triangles are similar using side, angle, side. Whenever you have a graphed problem, like problem number 3, First thing I would do is label everything that I can count very easily. Remember, diagonal lines that don't go straight up and down, you can't count. You would have to do Pythagorean theorem for that, and we don't need to do that if we can get away with it. What we're trying to find is which triangles are similar. So let's count. Horizontal or vertical lines are super easy because you just count the number of blocks. So this little guy right here, length of 1. From D to this middle spot, 2. From B to A is 1, 2, 3. And all the way down from B to E, 1, 2, 3, 4, 5, 6. Yep. Now, it may be helpful to draw this differently. So here's how I would redraw this. Boom. Now what did I do? I took all of these triangles. Each one has a short side and a long side, and I made them all face the same direction. I redrew them and I split them up. Why? Because it's very easy to see which ones match. You are looking for a scale factor. So let's look at the little one. It has a ratio of its own sides of 1 to 2. If you were to simplify that and put it in the calculator, the decimal is 0.5. The fraction doesn't get any simpler. So the ratio of sides of just this triangle of the short leg to the long leg is 1 to 2. If you check here, it is a ratio of 2 to 3, which is approximately 0.6. That's not the same. So we know the small triangle is not similar to the middle-sized triangle. Let's check this last one down here. This has to match one of the two. So 3 over 6. When you simplify that, it also gives you 1/2, which also gives you 0.5. So what that means is this triangle has the same ratio of sides as this triangle, and if these are right angles, these two are similar triangles by using side, angle, side. So now the last thing we have to do is find the statement that matches these up in the right order. We need one that matches CBD with ABE. Not that one, not that one of these two. And you'll look, they're trying to be tricky. See how we have CBD is similar to, and they switch the order of them? So check it out, CBD. Let's follow that in order. CBD. We cross the short side, we hit the right angle, we hit the longer side. We have to do the same order here. So if we look down, short side, angle, longer side. ABE needs to match CBD. Letter C. Finally, a company is creating a new cylindrical container to replace its original cylindrical container. Keyword, cylinder. So as soon as I see that, I would go to my formula sheet and get the formula, because we're dealing with volume, here. So the volume of a cylinder is pi times r squared times h. The new container will have 4 times the volume of the original container. The new container will have the same height as the old one. So this is going to be a problem where you have old versus new. Here's what I would do. Plug in numbers for these. Pick a number bigger than 3 for both the radius and for the height. Start with old, right? The only thing we know about old versus new is that new has 4 times the volume and that the heights are the same. So check this out. If you do pi times r squared, pick a letter for r, or excuse me, pick a number for r. Let's just go with 4. If we go 4 squared times, let's pick a number for height. Let's make it 5. This is all multiplication, so if you do pi times 4 squared times 5, you end up with approximately 251.327 ... There's a lot of decimals because we're dealing with pi. If you divide that number by pi, you end up getting 80, which means this number is 80 pi. So what does that mean? Okay, we know, since this is our volume, this volume is 4 times smaller, meaning the new one is 4 times bigger. So let's multiply this by 4. But let's just multiply the number. Let's keep that pi out of this because that's going to give us this gross nasty decimal. So 4 times 80 gives you 320 pi. This is equal to, again, that's our volume. So pi times our radius. Ooh, we don't know what the radius is. In fact, that's the answer to this question. So times our radius squared, which we don't know, times, oh, the height will be the same. Let's keep this 5. Okay, well, if I'm solving for a variable, just think of that like your x or an x squared. Divide by all these numbers multiplying it. Divide both sides by pi. They'll cancel out. You're left with 320 equals 5r squared. Divide by 5, because you cannot take the square root yet. Got to solve for r squared first. You get 64 equals r squared. Square root, you get r equals 8. So our final answer, if our original radius was 4, our final radius is 8. That means the length of the radius of the new container is f, twice as long as the radius of the old container.